My personal Shivaji from E&C department last year. My college name is Jain College of Engineering, Koran, Pune. I'm at Internet Emertxe Technology, Bangalore. My project name is Real-Time EV Monitoring and ADAS Driver Assistance System. In that module, AV ADAS dashboard. In multiple function and component are used. Software tools are in that STM32, Build, uh, but please, lab 3, Python dashboard.
And the major problem is, before discussing the implementation, let me explain why this project is important. Modern electric vehicles continuously generate a huge amount of information. This includes vehicle speed, battery, state of charge, motor temperature, motor torque, driving range, obstacle distance, and many other parameters. If engineers monitor each parameter separately, it becomes difficult to understand the overall condition of the vehicle. Important safety events like collisions or blind spot detections can easily be missed. To solve this problem, I developed a unified EV ADAS dashboard. This dashboard collects all vehicle information into a single interface. It displays speed, battery percentage, remaining range, motor temperature, ADAS collision warnings, blind spot detection, and fault errors in real time. The system also supports different drive modes such as eco, normal, and sport. Based on the severity of the detected danger, it generates four alarm levels: none, advisory, warning, and critical. So instead of monitoring many individual sensors, the driver or engineer can understand the entire vehicle status from one dashboard. This slide explains the overall architecture of my project. The project consists of four main stages. The first stage is sensor section. Here, potentiometers are used to simulate the accelerator pedal, brake pedal, motor temperature, and battery state of charge. Ultrasonic sensors are used to measure the distance between the vehicle and nearby obstacles. The second stage in the STM32 Bluepill microcontroller. This is the brain of the system. It reads all sensor values through ADC and GPIO pins. It runs different software modules such as EV control, ADAS engine, and fault handler. And EV control module calculates speed, motor torque, battery consumption, regenerative braking, and vehicle range. The ADAS engine continuously checks obstacle distance and determines whether the collision warning or blind spot alerts should be generated. The fault handler monitors abnormal conditions like motor overheating, low battery, sensor failure, or communication failure. The third stage in UART communication is for every 100 milliseconds, STM32 sends two structured telemetry packets through UART operating at a 115200 baud. The fourth stage of the Python dashboard. The Python application receives the UART packets, extracts all information, and displays it graphically using matplot library. And the next slide. This slide shows the complete development roadmap of my project. Instead of developing everything at once, I divided the project into 9 phases so that each module can be tested independently before integrating them. The first phase was setting up the development environment. I installed STM32 Cube IDE for firmware development, PiximLab for hardware simulation, and Python for creating the dashboard. The second phase was configuring STM32 peripherals such as GPIO, ADC, timers, UART, PWM, and interrupts. The third phase focused on reading sensor inputs through the ADC. Potentiometers were used to simulate acceleration position, brake position, motor temperature, and battery state of charge. The fourth phase was developing EV dynamic module. This module calculates vehicle speed, motor torque, regenerative braking, battery consumption, and driving range. The fifth phase implemented the ADAS system using 3HC SRO4 ultrasonic sensor. This module provides power collision warning, blind spot detection, parking assist, and time to collision calculations. The sixth phase added the fault detection and alarm systems. It continuously checked for abnormal situations like overheating, criticality, low battery, collision, sensor failure, and communication failure. The seventh phase developed the UART telemetry protocol to transmit vehicle data from STM32 computer every 100 milliseconds. The eighth phase implemented a UART shell. This allows the user to manually change vehicle parameters such as speed, battery percentage, motor temperature, and drive mode without changing the hardware inputs. Finally, the ninth phase developed the Python dashboard using MATLAB to visualize all incoming telemetry data in real time. Next thing, environment setup and GPIO peripherals. This slide explains the software tools and STM32 peripherals used in the project. In phase 1, I prepared a software development environment. STM32 was used to write, compile, and debug the Embedded program. MPLAB was used to simulate the STM32 blue pill board along with potentiometers, LEDs, ultrasonic sensors, and serial communication. Python 3 was used to build the dashboard application. The Matplotlib library creates graphics and gauges. NumPy performs mathematical operations, and PySerial receives UART data from STM32. And after preparing the software, I configured STM32 peripherals. Timer 1 generates 10 millisecond interrupt that updates the EV dynamics. Timer 3 generates 100 millisecond interrupt to periodically sample sensor values. Timer 2 works with microsecond resolution and measures the echo pulse width of HC SR04 ultrasonic sensor. Timer 4 generates PWM signals that control the buzzer used for alarm conditions. The ADC reads three analog inputs connected potentiometers representing the accelerator pedal, brake pedal, and motor temperature. And next thing, ADC sensor inputs and EV dynamic model. This slide explains how vehicle inputs are collected and how EV model is calculated. The first part is the ADC sensor system. Three potentiometers simulate im- important vehicle inputs. The first potentiometer connected to PAO and second to PA1 and third to PA2 and STM32 used a 12-bit ADC which produces values from 0 to 4095. These raw values are converted into engineering units that can be used by EV model. The sensor values are sampled per every 100 milliseconds using timer 3 interrupts. The project also includes software functions like EV inject speed and EV inject SOC, allowing the developers to directly set speed and battery values during testing without changing the potentiometers. The second part is the EV dynamic engine. Using accelerator and brake inputs, the system calculates motor torque. The torque ranges from 0 to 250 newton meters depending on selected drive mode. And later on, this slide explains the advanced driver assistance, which is the mainly safety feature of the project. The system uses three HC SRO4 sensors. One sensor is mounted at the front and another at left side, left blind spot, and right side as right blind spot. The STM32 continuously reads the sensor measured by all three sensors. Based on these distances, the current vehicle speed, the ADAS module decides whether it should warn the driver. The first feature is forward collision warning, and if the front obstacle is closer than 50 centimeters, the system generates a warning, and if the system less than 20 centimeters, it it shows alarm is generated and higher priority. The second feature is time to collision, and third feature is blind spot detection. And next thing, fall detection and alarm priority system. This slide explains how the project detects the faults and manages alarm priorities. Apart from monitoring obstacles, the system also checks whether the vehicle itself operating safely. The project stores faults inside a single 8-bit variable called fault register. Each bit represents one fault. Bit 0 includes motor over temperature, bit 1 includes battery state of charge is critically now, And bit 2 indicates critical collision. Bit 3 represents ultrasonic failure. Bit 4 represents UART communication failure. And next thing, alarm priority. The project also defines 4 alarm levels. Alarm none. This means everything is normal. Alarm advisory. This is the lowest priority. It is used for situations like overspeed and blind spot detection. Alarm warning. This indicates a potentially dangerous situation. For example, obstacle is less than 50 centimeters. And alarm critical. This is highest priority. It occurs when obstacle is closer than 20 centimeters. And next thing, UART element plot. After calculating the vehicle parameters, the STM32 sends the information to through computer through UART communication. STM32 transmits data for every 100 milliseconds, which means the dashboard updates approximately 10 times every second. And the Python application continuously reads these test frames, which are include here speed, SOC, torque, temperature, range, acceleration, brake, etc. It separates each field using labels. Finally, it updates the dashboard in real time. Next thing, this is our code for EV dashboard. And here we are using ADAS.h, common.h, evcontrol.h, and many other header files and source files. Initially, overall project structure is that this project developed from electronic vehicle driver assistance system using STM32 F103C8T6 Bluetooth microcontroller. Instead of writing everything inside one folder, this project is divided into multiple header files and source files. Each file has specific responsibilities such as controlling the EV, reading ultrasonic sensors, faults, etc. Initially, here common.h, if we see this, it acts as the function of project because almost every other file includes it. It imports important STM32 HAR libraries and standard C libraries like stdint.h, math.h, and stdio.h. It also defines commonly used macros such as clam to limit values with a range and array size to calculate the number of elements in an array. In addition, it stores common constants like drive modes and vehicle states so that every module uses the same definitions throughout the project. And here, if we observe ultrasonic dot h and ultrasonic dot c and ultrasonic dot c, wait, ultrasonic dot h and ultrasonic dot c. These files are responsible for communicating with three HC SRO4 sensors. As we all know, one is placed at front and one is right, one is left. And HCSR4 ID enumeration assigns an ID to each sensor, while the HCSR04 sensor underscore T structure stores the GPIO ports and pins used for trigger and echo signals. The sensor array contains the hardware configuration of all three sensors, making easy to access each one using ID. Next thing, EV control dot H. EV control dot H. Electrical vehicle simulation. This module represents the vehicle itself. The EV handle type def structure stores important vehicle parameters such as accelerator pedal position, brake pedal position, vehicle speed, motor torque, motor temperature, battery state of charge, regenerative braking, etc. Next thing, ADAS.h. ADAS.h. Wait. ADAS.h. Advanced Driver Assistance System. It is the intelligence of the project. It continuously monitors the vehicle speed, distance measured by ultrasonic sensors to detect dangerous situations. It defines different alarm levels, alarm advisory, alarm none, alarm warning, alarm critical, etc. Next thing, if we see fault.h and The fault management module checks whether the system is operating safely. It defines different fault flags such as motor over temperature, critically low battery SOC, and critical collision detection. These faults are stored inside a fault underscore handle typed of structure using a bit mask, allowing multiple faults to be active at the same time. Functions like fault underscore init, fault underscore check, and fault underscore clear initialize the fault system, continuously monitor vehicle conditions. And here, if we observe uh, main.h and unishell.h, UART shell.h. Main.h file is generated by STM32 IDE and contains GPIO pin definitions and basic project configurations used used by entire application. The UART shell file implements the serial command interface over UART. Over UART. And now let us go through our working models. And here IO frequency megahertz I set as 8 and it is 31.25. And I just load the bin file. I don't know why it's closing. Yeah, here the way it comes, it's present speed, SOC, torque, temperature, ring, range, acceleration, brake, etc. based on the things that I have set it here. And here, when I reduce the brake and when I increase this acceleration, if we observe this IO port, it is simply showing that brake, where is the brake? Um, acceleration, brake. Yeah, brake is decreased to 34 and acceleration is increased to 95. And clearly, if we observe time to collision is 0, speed is also increasing with respect to acceleration. And now here the front distance is very low. So it is showing the red light and the warning also. And here the left distance and right distance is completely based on the speed is if the speed is greater than 20 kilometers per hour and the vehicles are near, then we can observe this blue light and green light also will glow. And based on these sensor values, we can easily wait a second. And here in command prompt, in command prompt, I just go through this and cd percentage user profile percentage dash downloads. cd percentage user profile percentage. Mm, wait a second. And here copy CD EV dash CD EV dash and ladder com 2. And here, if we observe in this, the front distance is very low. Because of that reason, we observe EV dashboard alarm is critical and this background is changing based on that. If I increase this front distance and there is no vehicle, then there is no alarm and there is no red light. And if we go this, everything will be fine. And we can see clearly this torque, acceleration, brake, motor temperature, alarm, fault, and signal. This is the battery percentage available right now. And this is the speed history. And now, if yeah, if I reduce this acceleration, even if I increase this brake pedal, and if we observe when I increase this temperature also, there is a warning signal, fault signal. And okay, then I'll decrease it right now. And now, if we observe this condition, automatically, initially we have seen it is 10 kilometers per hour, but when we decrease it to 0, and automatically we can observe the acceleration is reducing. And here we have set an brake pedal to very high. And here we clearly observe that torque is negative minus 56 newton meters, acceleration is 0, brake is 100, and water temperature is 40.7 degree, alarm none, fault nothing, signal on. And if this is the EV vehicle and if it goes greater than 20 kilometers per hour and this vehicle is near to this vehicle, then we can observe again that fault condition regarding that. And now, yeah, we can observe this. I am decreasing this SOC, and simply we can observe and torque is minus 56, brake, motor temperature, alarm fault, and signal. And when I reduce the temperature this much, and we can see the motor temperature is reduced to 25 degrees Celsius. And later on, when I increase this acceleration pedal and decrease this brake pedal, everything goes right. And this we can see brake is 50 percentage. And here what I did is brake I kept at correctly at the center of 1.68. At this time, if we observe this, torque is changed to minus 28 nanometers and acceleration 100 percentage. And now we can observe this IO virtual term also. Here, every two lines are updating equally, and we can observe time to collision also simply here. And if there is any fault, we can observe this alarm warnings. This is very effective method for real-time application. Everyone can easily monitor the things. And here, I this is the efficient way to create and deploy easily for the electrical vehicle users to monitor their driving regularly. And if it is possible, we can also add parking assistance also too. And finally, this is the complete project that we have deployed, and now you can observe speed history also. To conclude, this project successfully demonstrates a real-time electrical vehicle ADAS dashboard using STM32 Bluepill microcontroller, MPLAB simulation, and a Python-based dashboard. The system integrates EV dynamics, ultrasonic-based ADAS features, fault detection, UART telemetry, and live visualization into a single platform. It provides important safety features such as forward collision warning, blind spot detection, time to collision estimation, and multi-level alarm systems. The UART shell also allows easy testing by injecting different vehicle parameters. Overall, this project helped me to gain practical experience in embedded systems, STM32 programming, sensor interfacing, UART communication, real-time data processing, and Python visualization. In the future, this project can be extended by replacing the simulated sensors with real hardware, adding CAN bus communication, GPS, camera-based object detection, and cloud connectivity for advanced smart vehicle applications. Thank you for your time. I'll be happy to answer your questions. Thank you.